Hello everybody, welcome to your 9th lecture in physical geology. This is Dr. Hurt. We're going to be talking today about metamorphic rocks. So we did igneous rocks, now we're going to be moving along to metamorphic rocks, one lecture on this, and then after that we're going to move on to our last rock type, sedimentary rocks, which is going to take at least 2 lectures. And sedimentary rocks are kind of big can of worms. So anyway, but metamorphic rocks today. And so you have a beautiful picture. Has anyone ever seen rocks like this, actually? You can see how beautifully folded they are like that. Did you ever think that rocks could fold? Well, there you go. There you have it. You can see the folds in the rocks, right? So we're going to talk about how things like that happen, which are kind of weird, right? You probably don't think about rocks folding. So anyway, metamorphic rocks, what are they? That's the first question, right? What is a metamorphic rock? Well, metamorphic rock is one, you got the definition right down here. So metamorphic rock are rocks that are modified due to high pressures and temperatures. Okay, so an igneous rock, we talked about that in the beginning. It's one that forms from a melt, right? You got molten rock, and then it solidifies, crystallizes, makes a solid rock, right? So that's an igneous rock, right? Forms from a melt. What's a metamorphic rock? Well, it is one that is modified, changed somehow due to pressures and temperatures. Okay, so metamorphic rocks are some of the oldest rocks on Earth, and that maybe makes sense because as rocks get older, it's more likely something's going to happen to them. They're going to be modified somehow. They're going to experience metamorphism. So the oldest rocks we have on Earth, the Costa Gneiss, right there. It's in Canada, close to. It's also in Greenland, by the way, so it's close to the northwest. Canada, so it's over 4 billion years old. Okay, Costa Gneiss. Gneiss is a type of metamorphic rock we'll learn about later. Okay, now metamorphism. What the heck is metamorphism? So metamorphism, this is something you got to know. Do I have a question about this? No, maybe I don't actually have a question about what is metamorphism, but something very important to understand is that it is a collection of solid state processes which modify a rock without melting it. Okay, now important thing here is solid state. So solid state means that it doesn't melt. If it melts, what is it? Igneous rock, right? So if it melts or partially melts, it's an igneous rock by definition. If you just have solid state metamorphism, meaning that it never actually melts, it just changes in the solid state, that means you're in metamorphic rock territory. Okay, so you modify a rock. By the way, important word here. I hope you're listening, okay? If you're tuning out, listen now. It's an important word. Protolith. Remember protolith. Metamorphic rocks, protolith. What's the protolith? Proto means beginning. Lith means stone. So protolith is just the starting stone. It's what you start off with, gets metamorphosed, and then it turns into a metamorphic rock of some kind, okay? So how does metamorphism occur? This is something we're going to study in more detail as we go forward. It happens, so these are your agents of metamorphism. I actually asked that here. Which number is it? You can kind of skip ahead if you wanted to. Number 14, I say, what are the agents of metamorphism? Well, it's these 3 right here. Temperature, pressure, and fluids. Okay, so any 3 of those things can be the cause of metamorphic changes in a rock. Okay, so we also have low to high grade. We're going to talk more about the grade of metamorphism. That's basically how much metamorphism has occurred, whether it's a low amount of metamorphism or high amount of metamorphism. We call that low to high grade. And what can change? That's another question we actually talk about a little bit later. Can't remember. See, it looks like it's number 13. What are some of the things that can change? Okay, and you could actually put this in for number 13, but you have to kind of explain it in some detail. You can't just put single words there. You notice I put in bold, please explain each change. So grain size changes, shape of the minerals change, the mineral content changes. We also get foliation, and probably going to have one more thing there too. Okay, so. And where does metamorphism occur? It happens in any kind of tectonic environment. We'll talk more about all these things later. It's just kind of an overview of what we're going to study right now. All right. So number 2 says, if you raise the temperature of a rock to the melting point, you let it cool after it partially melts, what kind of rock do you have? Well, you don't have a metamorphic rock anymore. You have an igneous rock, right? Because igneous rocks are rocks that have melted and then they cool from a melt. Okay, now number 3 and number 4, this is what we're going to talk about right now. Where are typical pressure ranges and typical temperature ranges. Remember, it's high temperatures and high pressures that metamorphose. They're the agents of metamorphism. That's what causes the metamorphism. So what temperatures are we talking about? We're talking about in the range of 250 to 850 degrees Celsius. Okay, so very hot. 250 degrees Celsius is something maybe like, imagine like a pizza oven. Okay, 100 degrees Celsius, remember, is boiling point of water. So if you're at 250 degrees, it's pretty hot. It's maybe like 500 degrees Fahrenheit. It's pretty hot. Think of a hot oven. 850 degrees is getting to the point where things are like red, glowing hot. Okay, not quite maybe melt enough to melt a rock. Usually rocks melt starting at around 1,000 degrees Celsius. But that can change. One thing I want to point out to you: water lowers the melting temperature of rocks. So rocks can melt at 650 degrees Celsius if it's wet. There's water, but if water is not present, you need like 1,200 degrees Celsius. Okay, so you can't get too high, because if you get too high, you're no longer in the area of metamorphism, then because it'll melt, right? Okay, so temperature in the Earth increases by 20 to 25 degrees per kilometer. Okay, so it gets hotter as you go down into the Earth. So it says, number 7. How much does temperature increase per kilometer in the Earth? 20 to 25 degrees. Okay, 20 to 25 degrees. So you can imagine if you go down 10 kilometers, right, you're at 200 to 250 degrees Celsius. That's when you start getting metamorphism. Okay. Now, what about pressure? Okay. Pressure is the amount of force that you feel per square inch on your body. So it's a force per area. So actually right now, whether you know it or like it, you're actually feeling about 15 pounds per square inch on your body right now, just from the weight of the atmosphere sitting on top of you. Of course, in the Earth, you got much higher pressures, because instead of just having the atmosphere sitting on top of you, you actually have the rocks sitting on top of you, which weigh a lot more than gas, right? So at 5 to 30 kilometers depth, you have 1.5 to 10 kbar. What is a bar? Now, I just mentioned you have 15 pounds per square inch. You ever heard of PSI? Maybe if you check the pressure level in your tires, it's usually around, like, if you're lucky, it's around like 30 psi, right? 30 pounds per square inch. Well, 15 pounds per square inch is just normal atmospheric pressure. Okay, so normal atmospheric pressure, what you feel right now, is actually, we use a different unit in science. We use something called a bar. So 1 bar is normal atmospheric pressure. 1 bar. Okay, so right now you are feeling 1 bar. Unless you're scuba diving, and maybe if you're scuba diving, if you go down 10 meters down, about 30 feet down, that'll add another 1 bar. So you would feel about 2 bars. It's amazing, because when you go down into the water, I get down to about 10 feet, and man, it really hurts my ears. You could feel the pressure in your ears, right? So those of you who dove underwater, you know what I mean. But that's only maybe 2 bars of pressure instead of 1 bar of pressure. Okay, so it's just double what you feel on the atmosphere. When you go down, you have 10 meters of rock, just 10 meters of rock sitting on top of you. You're at about 3 bars. If you go down 1 kilometer, that's deep into the Earth, right? You have 300 bars. Okay. Now remember how kilos work, right? Kilos, a kbar, 1 kbar equals 1,000 bars, right? So 300 bars is equivalent to 0.3 kbar. Okay, so if you go down 1 kilometer, you're about 0.3 kbar. Okay, so how much does pressure increase per kilometer? Do I ask that? I think I might. What is typical pressure ranges under which metamorphism occurs? Number 4 says, what are typical pressure ranges? We usually need about 1.5 to 10 kbar. Okay, 1.5 to 10 kbar, and that corresponds to 5 to 30 kilometers depth. Okay, how deep is the crust? Do y'all remember how deep the crust is? Usually on average about 30 kilometers. Okay, so this is all stuff that's happening above the mantle, okay, in the crust. All right, so hope that all makes sense. 30 kilometers, you have 9 kbar of pressure. Okay, so that's 9,000 times the normal atmospheric pressure. Okay, so how much does the temperature increase per kilometer? Or how much does temperature increase per kilometer? We said 20 to 25 degrees Celsius. What is the pressure at 5 kilometers depth? 5 kilometers depth, 1.5 kbar or 1500 bar. What's the pressure at 30 kilometers depth? 9,000 bar or 9 kbar. Okay, so hopefully that all makes sense. We answered everything up to number 8. Okay, number 8. All right, so that's pressure and temperature in the Earth. Just to kind of give you some ideas, if you're at the beach, probably going to be about 25 degrees Celsius. Okay, so that's kind of normal, like a hot day, warm day. It's going to be 25 degrees Celsius. That's to kind of give you an idea about what Celsius means. Okay, if you go down deep into the Earth, like a gold mine, temperature can be quite high, maybe about 60 degrees Celsius. You cannot survive down there very long. Your body is the temperature of your body is about 37 degrees Celsius. So once you're at 60 degrees Celsius, that's really hot. You can't survive down there too long. So they have to have some kind of cooling system there. A pizza oven's about 350 degrees Celsius, a really, really hot oven. Probably your home oven gets around 250 to maybe 300 degrees Celsius. Okay. So temperature increases by 20-25 degrees Celsius per kilometer. Temperature at 5 kilometers, it's 100 to 125 degrees Celsius. Temperature at 30 kilometers, about 600 to 750 degrees Celsius. Okay. So if you're a rock and you get buried, if you get down to 5 to 30 kilometers, that's when metamorphism starts to occur. Let's talk about a little bit more about pressure here. Okay, so standard air pressure, like I said, is 1 bar. The Chilean mine, I don't know, probably y'all don't remember this. This is now a long time ago, but it was pretty dramatic when it happened. But, it was 300 bars was the pressure down there, right? So it was a very deep gold mine there in Chile. So pressure can be quite... Of course, when you're down there, you don't actually feel 300 bars of pressure, but the rocks, the overburden on top of you is about 300 bars. Okay, so... that's about 1 kilometer depth. That's 1 kilometer deep mine. Okay, so just to kind of give you an idea, 50 African elephants sitting on a chair, that would be about 2,000 bar. Okay, so it would be enough to metamorphose a rock, right? Of course, you could never stack 50 African elephants on a chair, but just kind of something for your imagination. All right, so metamorphism. You start off with sediment, like mud, and you can compress that sedimentary rocks into a shale. Okay, so shale is just a mud rock. We'll talk more about shale next lecture. We talk about sedimentary rocks. So that rock that you start off with is called the what? Protolith. Make sure you know protolith. Protolith is very, very important. All right, so shale is the protolith. It starts off as mud, turns into shale after normal sedimentary processes. Then what happens is when you increase the grade of the metamorphism, that means the metamorphism gets higher and higher, higher pressures, higher temperatures. You go, go to number 9 on your lecture assignment. You go from a shale to a slate is low grade. Phyllite is kind of a higher grade. Schist is a medium grade. Finally to a gneiss, and that's the highest grade. Okay, so those are the 4 rocks you have to know for that. What happens when you take a limestone? Limestone is a sedimentary rock that is made out of calcium carbonate, calcite. Starts off as the bodies of marine organisms and shells from marine organisms. Okay, it turns into a limestone by normal sedimentary processes. And that limestone will ultimately turn into marble when it gets metamorphosed with sufficient pressure and temperature. Okay, so... what do you get when a sandstone recrystallizes? Okay, you go from sandstone. Sandstone is a sedimentary rock, and when it metamorphoses, you go to a quartzite. Okay, so sandstone could be maybe pure quartz, forms from the sand, like beach sand. Normal sedimentary processes will turn that into a sandstone, and then that sandstone will metamorphose, turn into a quartzite. Okay, so we answered everything up to number 12. All right, so now let's do number 13. We already kind of gave you the beginning answers in number 13 in the intro, But we'll talk about the specific changes that can occur during metamorphism. Okay, so the first change that can occur is something called recrystallization. Recrystallization is when the crystals recrystallize. Okay, and they usually become larger because guess what? Larger crystals are happier crystals. Crystals don't like to be small, actually. They're often small, but they don't like being small. They like to be as big as they can. I could go into the reason for that, but crystals always like to grow. They like to grow. So when they have enough temperature and pressure to grow, that's what they do. So you can go from tiny clasts of sand grains, and they will actually grow and crystallize, and they'll form this kind of interlocking grid of quartz crystals. And it makes a much stronger, tougher rock called quartzite. And quartzite, by the way, is a very tough rock, very hard, very difficult to erode. All right, so that's recrystallization. The crystals grow. Very simple, right? Another thing that happens during metamorphism are things called phase changes. Phase changes. Phase changes, it's this. When, you're a crystal, you can have the same chemical composition and different crystal structure, and you're a different mineral, right? So one example I gave you in the beginning when we talked about minerals. Do you remember this word? Polymorphs. Polymorphs. I talked about this when we talked about minerals, right? So polymorphs equals a crystal with the same mineral with the same chemical, or I could even put the same chemistry, same elemental makeup, different atomic structure. Okay, one example I gave that's very pronounced example is a diamond versus graphite. Diamond and graphite, what's the chemical formula of diamond? Chemical formula of diamond is carbon, pure carbon. What's the chemical formula of graphite in your pencil? Carbon. Okay, carbon, carbon. So those are polymorphs. Well, guess what? Diamond is denser. It's a more efficient way of packing atoms. So, you can imagine if you're ever like packing a car to go on a long car ride, or maybe packing your suitcase to go on a flight. What do? You've got to pack that, What do? You often fold your clothes, right? Why do you fold your clothes? Why don't you just stick all your clothes in a big pile inside the suitcase? Well, when you fold your clothes, that's a more efficient way of packing the clothes, okay? Save volume. Well, volume is, the minerals are always looking for a way to save in volume when they get buried down deep because it's high pressure there, right? Volume is, there's not very much volume to go around, okay? High pressures. So graphite, when it gets under sufficient pressure, it'll turn to diamond, okay? That's called a phase change. So what just happened there? Polymorphs switching from one structure to another structure that's more volume efficient. That's called a phase change. Think of arranging all of your clothes in your suitcase to make it more compact so you can fit more clothes in a smaller area. Okay, that's the phase change. So diamond does that. There's a lot of things that do that. Coesite is another form of SiO2. So quartz is one form of SiO2. If the pressure gets high enough, quartz will actually turn to another mineral called coesite. Okay. There's other things like aragonite, for example. I shouldn't put marble here, but aragonite. Aragonite is a more efficient form of calcium carbonate. So at the surface, you find a lot of calcium carbonate, calcite, but when you get down deep, there's a lot of pressure, you start to get aragonite. Okay. So that's phase changes. Okay, phase changes. Third thing you want to put down for number 13, and please explain each of these, right? You can't just put down a word. You got to explain a little bit what I mean or what you mean, okay? Third thing that can happen is called neocrystallization. Neocrystallization is when new minerals form, okay? So let me give you an example of that. You could have, for example, quartz and dolomite, two different minerals, and what will happen is they will actually combine and form a new mineral called pyroxene, okay? So quartz and dolomite, under enough pressure, can form pyroxene, and then it'll also form CO2 gas, which then can escape. Okay, so that's an example of neocrystallization. Okay, I do ask you, let's see. Oh, I answered number 15, by the way. I asked what's a polymorph, right? So you could give like diamond and graphite, quartz and coesite, calcite and aragonite. Those are all polymorphs, okay? Different pairs of polymorphs. All right, so that's neocrystallization. You have new minerals form. Another thing that can happen is called pressure solution. So pressure solution is when you get, this is what happens. Kind of interesting. So when you get a lot of pressure on a rock. Now let's zoom into the rock and look at the grains, the individual crystals in the rock. Let's say you have a bunch of grains like this. Okay, you all see these. And it kind of has this target bullseye sort of pattern just so you can kind of see how this pressure solution happens. When it gets put under sufficient pressure, sometimes at the grain boundaries, right there, right there, right there, right there. Okay, you see all those are the grain boundaries. What happens is that if there is a fluid present, like water, the mineral will actually dissolve along those grain boundaries. It'll actually dissolve along those grain boundaries. And so you can see what happens. It'll dissolve and it'll recrystallize in other places. So this shows what happens. You can see these round grains are responding to stress from the pressure and the pushing, and they're actually recrystallizing in kind of more of like a flattened elliptical shape instead of a round shape. Why do they do that? Well, because when you have stress coming from one direction, so let's say plates are pushing together, right, like this, you have stress coming from one direction, it's going to be better to have a flattened grain. It's more efficient way of packing the atoms, okay, packing the crystals in the material. So again, think of that suitcase packing the clothes in there, right? Then that happens, right? When you pack a suitcase, how do you lay the clothes? You lay them down flat, right? You don't lay them all stacked vertically like that. You lay them all down flat. That's the most efficient way. So the same thing happens with rocks, right? So this is kind of cool. This is called a metaconglomerate. So this is a rock that initially started off with spherical grains, spherical rocks. It's kind of composed of little smaller rocks. But you can notice that the squishing squished the shape of the rocks and made them more like elliptical or oval shaped, okay? So pressure solution occurs because many minerals are more soluble in water at high pressure, and pressure is often highest at the grain boundaries, and thus dissolution, so dissolving occurs on the grain boundaries, and it recrystallizes elsewhere, okay? So I know it's kind of weird to think of rocks as dissolving in water, but at high pressures, a lot of rocks do dissolve in water like that. Okay, so that's pressure solution. So that's kind of differential. Differential stress means stress from one direction. Instead of equal in all directions, you have stress coming from one direction. So pressure solution is differential stress, irregular squeezing when liquid is present. Okay, water has to be present to dissolve those grain boundaries away. All right, number 5 is plastic deformation. So this happens when rocks get close enough to melting. They're not melted, but they're close enough to melting to kind of start to act like silly putty instead of like a brittle rock. Think of the asthenosphere versus the lithosphere that we learned about in lecture number 4, right? So you can have rocks, they start to act kind of like silly putty instead of like a brittle rock, and they can actually fold, bend, deform, stretch, squeeze, whatever. They can do that and without cracking. So that's something that can happen. You can change the shape by squeezing it, okay? And it's gotten so plastic and elastic that you see it can get all these folds, and it can get, the grains can get squeezed like this. And so that's yet another thing that can happen when rocks get hot enough and high enough pressures. Okay, and I think that's number 5. So we did everything. Okay, so those are the 5 changes that can occur during metamorphism. Okay, so I already answered number 14. What are the main agents of metamorphism? Temperature. Okay, one thing here. Stop here for a second. I wanted to explain one thing. let's say that you have some sedimentary rocks like this in layers. You see the sandstone, limestone, shale, sandstone, all this stuff. And then a big intrusive magma body comes and intrudes into that. Okay, and so a bunch of magma moves into that area. That hot magma is going to raise the temperature of those rocks, right? And so often surrounding this igneous plutonic body, remember a pluton is that magma chamber that's underneath the ground, you'll get a ring of metamorphism. That is called contact metamorphism. It's high temperature, low pressure metamorphism. Okay, high temperature, low pressure metamorphism. So that's what contact metamorphism is. Notice I have something about that there. Number 19, I mentioned contact metamorphism, so you need to know what that is. Okay. So often the rock associated with contact metamorphism, high temperature, low pressure metamorphism, is called hornfells. Hornfells. Okay. Another thing is pressure. Okay, so when you just squeeze a rock, has high enough pressure, you can get you can get metamorphism, right? So that's the second agent. Temperature, pressure is the second metamorphic agent. Okay, so that's what you're putting down from number 14. Okay, so sandstone turns to quartzite. So this is like a microscope image of what sandstone looks like here on the left, right here. This is what the same sandstone looks like after it's metamorphosed. And you see how the grains have grown. They become kind of interlocking. There's no more like gaps or space between the grains anymore. They've cemented together and recrystallized. Okay, so that's pressure. That's effects of pressure. Pressure is so useful for, pressure causes, like we said, phase changes. Okay, remember I mentioned phase changes, polymorphs. I want to give you one example of a very important set of polymorphs that have this formula. Okay, so remember polymorphs, they're a set of minerals that have the same formula but different crystal structures. So this is a set of 3 different minerals. First is andalusite, kyanite, and then sillimanite. Okay, kyanite has this beautiful blue color, by the way. So they have this formula, aluminum 2, silicon O5. Okay, they're called aluminosilicates, aluminum silicate minerals. Okay, kyanite is here, andalusite's here, sillimanite is here, and this kind of diagram that you're looking at is called a PT diagram, a pressure temperature diagram. Okay, so minerals are so useful for us because we can look at the minerals that we find in a metamorphic rock and we can know about what temperature and pressure they come from. Okay. So, for example, if we find kyanite in a metamorphic rock, we know that the pressure must have been at least 0.2 GPa. Here's a new pressure word, GPa. What is a GPa? GPa is a gigapascal. Okay, it's a gigapascal. So 1 GPa is, you could think of it as about, so 1 GPa is about, well, I could tell you like this, about 100,000 PA equals 1 bar. So a 1 billion of that would be 10,000 bar. Okay, so that's about, you could see, that would be about 10 kbar. Okay, so you could see that you need at least 1 GPa is about 10 kbar. So here this is about 0.2 GPa, so it's about 200, right? 200 bar. Okay, so you need quite a bit of pressure right there. Okay, to create kyanite. Now let's say you find sillimanite, right? Well, you know that with sillimanite, the lowest temperature, for example, you could possibly have is about 500 degrees Celsius. Okay, for andalusite, you know that the temperature, had to be below 700, and I don't know what does that look like? 775, maybe 775 Celsius, and right? You had to have a pressure below maybe like 0.4 GPa, okay? So those are just kind of giving you some ideas about how we can use polymorphs to figure out some things about what the temperature and pressure was that the mineral, that rock formed at, okay? Hope that, I know it's complicated. But hopefully it makes some sense. The basic bottom line here that I want you to understand is that when we have minerals like this, these polymorph minerals, they can tell us what the pressure and temperature was of the metamorphic rock. And that's very useful for us as geologists, okay? So there you go. There's kyanite, sillimanite, andalusite. Changes in temperature and pressure change the minerals, and we can figure out, what pressure that rock must have been under. So there's a picture of diamond, okay, graphite. Those are polymorphs. If we find diamond, we know that that rock must have been under pretty high pressure, okay. So there's calcium carbonate, calcite, limestone changing into marble, etc., etc. Okay. So another thing we can have, right? I guess I only asked for 3 things for number 14, but you could also mention compression and shear stress in here. So compression and shear stress is different than pressure because pressure comes equally from every angle. Compression and shear stress only come from one direction, okay? So we'll get more into this when we talk about deformation in the earth, but for right now I kind of just lump shear stress and compression in with pressure. Okay, there is a difference, but we'll talk more about that in lecture 20. We'll talk about deformation. Okay, last thing here is hydrothermal fluids. Okay, so hydrothermal fluids can also metamorphose the rocks too. So hydrothermal fluids are very hot fluids. Now, when the pressure is high, water can actually get above 100 degrees Celsius. Remember, 100 degrees Celsius is the not melting point, the vapor pressure, the vapor point evaporating point of water, right? 100 degrees Celsius. But at high pressure, that can go up. So you ever hear of a pressure cooker? In a pressure cooker, you can get the temperature of the water very high because it's under pressure. Same thing with the earth, right? When you have water at very high pressures under the earth, it can get very, very hot. And hot water is always better at dissolving and changing chemistry and reacting with rocks. So it's highly reactive, and it can change the chemistry of the rock. And we call that hydrothermal metamorphism. Okay. Let's talk a little bit now about metamorphic grade. Okay. Number 17 says, what's metamorphic grade? It's just the amount of temperature and pressure and metamorphism that rock has experienced. So the higher the grade, the higher the temperature, the pressure, the hydrothermal fluids, and the higher the degree of metamorphism. So things that have experienced a little bit of metamorphism, we call that low grade. Things that we have experienced a lot of metamorphism, we call that high grade. Okay. So this little diagram is very useful for us. Okay. So this shows, again, this is a PT diagram, shows pressure in K bars with temperature. Okay. Now, you can imagine 3 different paths here. Now, I talk a little bit about these paths for number 19. Okay. Now, you have a pressure temperature diagram there in your lecture assignment that you have to kind of analyze. Okay. There are 3 different pathways you could take. You could take the high temperature, low pressure pathway here. Okay. Right? So you see this. This is the high temperature, low pressure PT path, pressure temperature path. Okay. That is called contact metamorphism. You could take, I'll get a different color here. I'll get the green color. Hey, I want this pen. How does this work? Pen color. Don't see how it works. Okay, whatever. Well, I wanted to use a different color pen, but I guess it's not cooperating. You could have the medium, the kind of like medium pressure, medium temperature regime. That's called mountain belt. There's a few names for this. Mountain belt metamorphism, mountain building metamorphism, or regional metamorphism. Okay, all those things kind of mean the same thing. It's kind of like the medium temperature, medium pressure pathway, PT pathway. So that's right here, okay, this one. Or you could have another pathway. This is the cold pathway, the low temperature, high pressure pathway. This happens at subduction zones. We'll talk more about subduction zones when we get to plate tectonics, okay? But that's where you have low temperature, high pressure, subduction zone metamorphism, okay? So I ask you in the, take a look at the diagram to the right, number 19. It shows metamorphic rocks formed from basalt protolith, different temperatures and pressures. So I'm just asking you, A, B, C, you see the three different pathways. Which pathway is subduction, which is mountain building, which is contact metamorphism, okay? So the high temperature, low pressure one is contact. The medium, kind of middle of the road, is mountain belt metamorphism, mountain building metamorphism, and the last one's subduction zone metamorphism. That's high pressure, low temperature. Okay, this is the facies diagram that you see. So what are facies? That's a weird thing. This is the diagram you see on your lecture assignment. What are facies? Facies is just kind of a, you could maybe think of it as the sort of like pressure temperature zones. Pressure temperature zones, okay? So if you take a basalt protolith, these are the different rocks that will form from that basalt protolith under different conditions, pressure temperature conditions of metamorphism. So if you take it to, let's go through the different facies. If you do a high temperature, low pressure contact metamorphism, okay, you will be in the Hornfels facies. Hornfels facies. Remember, we call that contact metamorphism. That's when you have rocks in contact with a, like a really hot magma body that's been intruded. That's why we call it contact metamorphism. That facies zone is called the Hornfels facies, okay? So we use facies as kind of like this. Like geologists can say, this rock, it is in the Hornfels facies. And everybody knows that when you say that, it means that it experienced high temperature, low pressure. Okay. If you go down the middle of the road, at low grade, you'll be in the zeolite facies. Then you'll be in the what's called the Pompelliite prehnite facies. That's that PP stands for prehnite Pompelliite. If you go to higher, kind of like medium grade metamorphism in the middle PT path, the mountain building metamorphism PT path, you'll be in the green schist facies, and then you'll get finally to the amphibolite facies, and you can even get to all the way to the granulite facies. But your granulite, you start to melt. Okay. If you go in the subduction zone PT path, you will spend most of your time in the blue schist facies until you get really high grade, and then you'll go to the eclogite facies. Okay. So anyway, facies, and this facies diagram that is for the basalt protolith applies to all metamorphic rocks. We use it. But it just tells you what the pressure temperature conditions were of that rock, okay? And we just use this diagram to describe to other geologists, hey, this is the pressure temperature that this rock experienced. It was in this facies, okay? So, when you hear green schist, you know that it kind of experienced middle of the road, mountain building type metamorphism, kind of medium grade metamorphism, okay? So that's how we use this diagram. And what's the thing about this diagram is you can even say, I hope I don't get this too complicated for you, but you could even say like, this marble is in the green schist facies. Does that mean it's a green schist? No. It's just in the green schist facies. It just means that it experienced intermediate grade metamorphism in a kind of a mountain building PT pathway. All right, maybe that's too much detail. I'm sorry if your mind is blowing up right now, but maybe that was TMI. But anyway, too much information, like too much geology information. Okay, so we'll just keep it there. So I answered everything except number 16. What is foliation? And do I just like not have a slide about foliation? Okay, here I just forgot to mention it right here. When you have compression and shear stress, and you have more stress coming from a single direction instead of just pure pressure where stress is coming from every direction equally, if you have pressure, you have shear stress where pressure is coming, or I should say stress is coming from one direction in particular, the minerals will orient themselves to in relation to that stress direction. And what happens is that creates, get ready to write this down, it creates a preferred orientation to the crystals. A preferred orientation to the crystals. And that's called foliation. Foliation comes from the same root word as foliage, like leaves. It literally means Latin for leaves. And you know that if you go look at the leaves on an autumn, well, not here in Corpus Christi, but somewhere else where there's fall colors, the leaves fall to the bottom of the forest floor and they form these, they all fall down flat, right? So it just means that there's this orientation, like flat orientation to the minerals in that rock that kind of remind the person of kind of leaves fallen on the ground, okay? So it's just a preferred orientation to the minerals. And that, when you see that, it screams, I have experienced shear stress. Okay, so when you see foliation, it says, I have experienced shear stress. So that means that the stress was coming from a certain direction, not equal in every direction, but a certain direction. Okay, we got through it all. I'm sorry. This is kind of a hard one, huh? It's kind of maybe hard to understand some of this stuff. But anyway, please contact me if any of it doesn't make sense to you. I know it's going to maybe be overwhelming, but please contact me. Let me know. I had somebody contact me today, say I'm struggling, and I called. I talked with this person on the phone for a while, and they felt better. They kind of felt, and you can do that. Look, I have a phone right here. You can call me. My phone number's on there. So whatever. But anyway, I hope that this was helpful for you. Lecture number 9. I'm going to tune out now. So thanks for listening, and you have a good week.